Hello, my dear friends. I am Dr. Tito, a Finnish word meaning knowledge. I always remain in search of knowledge, and I want to share with you what I have learned so far.
Today our target is to learn bond order, sigma molecular orbital and pi molecular orbital. So, and we are learning actually molecular orbital for diatomic molecules, and this is a part of that lecture. So at first we will learn what is meant by the bond order, because during our discussion bond order will be needed. Now bond order may be defined bond order may be defined in the following way. That is, bond order is equal to half of number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals. If you know the bond order of a particular molecule, then you will be able to say whether the molecule will be exist or not. Next, our target, we at first learn some definition, then we will come into the detail of the energy diagram for the molecular orbital. Next, our target is to learn what is actually meant by the sigma molecular orbital and pi molecular orbital. So at first we should learn sigma molecular orbital. So what is sigma molecular orbital, and you know what is sigma 1 and pi 1 from your higher secondary knowledge, 10 plus 2 knowledge. And here it is also same, that is, instead of bond we will just use the molecular orbitals. That means the definition will be like this: head-on overlap between two molecular orbitals two atomic orbital. Head-on overlap between two atomic orbital will give rise to a sigma molecular orbitals, just like sigma bond where there occurs head-on overlap, and you know sigma bond, due to this kind of overlap is much more better than corresponding pi bond where there occurs lateral overlap, and this type of bonding actually very strong. And this is in case of molecule we will say, so this is sigma molecular orbitals. And let me allow to clear this a little bit. Let's consider hydrogen molecule, that is hydrogen molecules, H2 molecules. In H2 molecule, you know, there occurs two hydrogen atoms. Say here one hydrogen atom, a nucleus of one hydrogen atom, here nucleus of another hydrogen atom. So two nucleus, and if we connect this will be the internuclear axis or molecular axis of the molecule. Now say here it is how this kind of particular orbital will be, sigma molecular orbital will be from the two atomic orbital of the hydrogen atom. Then you consider again here one nucleus, here there is another nucleus. Say this is 1s orbital of one hydrogen atom, this is one s orbital of another hydrogen atom, and the sign of the wave function, you know, the actually the atomic orbital is nothing but different wave function which is obtained by the solution of the Schrodinger equation. Now if the sign of the two orbitals be same, then two atomic orbital be same, in that case there will occur bonding interactions, and that bonding interaction will lead to a stronger bond leading to the formation of the molecules. So this is one 1s orbital, this is another 1s orbital of the hydrogen atom, and this is H2 molecule. This is one hydrogen atom, this is another hydrogen atom, and this is H2 molecule. And here what will happen, in between the two nucleus, the whole positive charge will generate, the whole positive charge will be concentrated or accumulated in between the internuclear axis. So one nucleus will attract the electrons of the other nucleus, other atom, and another nucleus will attract the electrons of the other atom. So in this way there will occur a bonding interactions, and the bonding electron will be concentrated in the middle of the two nucleus, so that two nucleus can attract the electron, and in this way a bonding molecular orbital will be formed. And this is the pictorial form of bonding molecular orbital. And since this is sigma type of interaction, so we'll call that sigma molecular orbital, and it is designated as sigma. In subscript there should be 1s, so sigma 1s molecular orbital. This is nothing but sigma 1s molecular orbital for hydrogen atom. Now if we consider another molecule, say lithium, and in that case lithium has atomic number 3, and in that case, so 2s or 2p orbital will also be involved during the formation of the bond. And on those cases what will happen, we can also consider the sigma bond formation of between the p orbitals. But before that you must learn another thing between two 1s orbital, that there may occur formation of the there of course occurs the formation of the sigma star molecular orbital, that is antibonding sigma molecular orbital. Antibonding sigma molecular orbital, how it will be formed? I am erasing the canvas. Antibonding molecular orbital, how it will be formed? So in this particular case, so this is 1s, say this is 1s, and this is nucleus, this is 1s, this is say another 1s, this is another 1s, but now the sign is opposite. So since the sign is opposite, so here not bonding interaction will occur, but antibonding interaction will occur, leading to the formation of the sigma star molecular orbital. See, this is one nucleus, this is another nucleus, and this is the internuclear axis or intermolecular axis. So here the electron will be actually go away from the nucleus, or so positive, or it will go in the outward direction. So in between the nucleus there occurs no accumulation of charge in between the nucleus. So this is not a bonding interactions, rather this is antibonding interactions. Antibonding, and this type of antibonding molecular orbital should be designated as sigma 1s, and in the superscript there should be one star. This star sign is used to designate always the antibonding molecular orbital, whether it is 1s or 2s or 2p, etc. In case of to designate the antibonding molecular orbital, we must put an asterisk sign. So this is sigma star 1s molecular orbitals. Another is, say this is a px orbital. Let me clear this. And exactly, so this is px orbital, 2px, and say this is again a 2px orbital. Okay, lithium onwards molecule will have 2p orbital, and say x-axis is the intermolecular axis or internuclear axis, and there occurs a nucleus here, and there occurs a nucleus here. So you see here also, if this charge be positive negative bonding interaction will occur, and this is also another type of sigma bond, and the pictorial formation will be like this. This is one nucleus, this is another nucleus, and since it is bonding interactions, so in the middle there will be accumulation of the positive charge, and in the outside there is a small amount of other charge. So this is negative. So this is actually 2 sigma 2px star. Sorry, not star. I'm erasing this. Not star. Star will not be there. Yes. So this is sigma 2px atomic orbital, molecular orbital. So this is sigma 2px molecular orbital, and it has, since we have chosen the molecular axis as the x-axis, so 2px will interact among themselves to form the sigma 2px, and in the similar way there will also occur the formation of the sigma star 2px, and the pictorial form will be like this. So here the opposite sign will be there, here plus and here minus, opposite sign of the wave function, that is orbital, will be there. So if you just draw now in the internucleus distance, what will happen? So this is negative, this is positive, will be very low in amount, again here it is positive, and here negative is very less in amount. So in the middle of the two nucleus, if you draw the nucleus in this way, in the middle of the two nucleus there occurs a very less amount of the negative charge of the electronic charge, and this is actually nothing but sigma 2px molecular orbital. Now I am coming to the pi molecular orbital, and you know in pi molecular orbital there actually occurs lateral overlap between the two atomic orbitals. If we consider say along x-axis the molecular axis, then 2px orbital, as we have told earlier, will form the sigma bond, but remaining 2p orbital, that is 2py or 2pz orbital, will then be parallel to each other, and lateral overlap is then possible. So, and in that case pi bond will form, or pi molecular orbital will be formed, and the pictorial representation will be like this. Say this is, so I am talking about now pi molecular orbital, pi MO. So pi MO is generated how? Lateral overlap between two atomic orbitals. Lateral overlap between two atomic orbitals will give rise to pi molecular orbital. So just like in the previous class, here pi star also be generated in the same way. Let us draw some pictorial form of the pi molecular orbital. So this is, say, py, okay, plus minus, say this is 2py, and this will be, say, plus minus, say this is another 2py. Okay, this will combine among themselves, and this, see, this is one nucleus, this is another nucleus, this is internuclear axis. So in between the two nucleus, in the above and below the internuclear bond, so the positive and negative charge will the electron density will be higher in between the internuclear axis of the two px orbital, and that is why a bonding interaction will occur, and this type of bonding is not along the axis. So this is lateral overlap, and this will be termed as the pi molecular orbital. This is actually 2py pi molecular orbital. Similarly, we can also draw in the same way, say this is plus, this is minus, and this is minus, this is plus. So here plus, here minus, so antibonding interaction will occur between these two py orbital. Antibonding interaction will occur, and in this way the pictorial form is like this. This is plus, this is plus, and this is minus, and similarly this is minus and this is plus. So this is actually, when you see in the middle there occurs no accumulation of the electron density, so it is antibonding interactions, and it should be designated as pi star 2py. Star should be in the superscript, and 2py, that is the atomic orbital from which this molecular orbital has been formed, should be written in the subscript. So this is pi star molecular orbital. So this is the different pictorial form of the molecular orbital, where the electron actually reside after the formation of the molecule. But you know, for our exam purpose, if we focus our exam, this drawing of the molecular orbital is not very important, but the important is the relative energy diagram of the molecular orbitals in a molecule. And if we then form the electronic configuration of that particular molecule in the different molecular orbitals, then we will be able to predict many things, and we can explain many experimental behavior, like we can predict whether the particular molecule will exist or not, or we can say whether the molecule is diamagnetic or paramagnetic, etc. In the next class we will discuss in these directions. And with that, thank you.